Hello, this is Colin Winsing from the Gatos Rocketry Club, and today I'm going to be talking about the flight controller code. This is the code that we used for our flight controller named Shoot, and I'm just going to be giving a real brief run over. This is 99% done. There's a few things here or there that aren't implemented. I'm just going to talk about, excuse me, the main things about it, so that way if you're looking to make your own or just curious how to get started, you have a basis. So here we are in the Arduino Editor, and this is all designed to run on a Teensy 4.1, so keep that in mind. So up here we're just including our libraries. These are for our external Eprom. Well, this is for the SD card on the Teensy. This is the servo that opens the hatch, and then these three are our sensors here. This we changed, so if you notice, I should have mentioned this at the beginning, we have these comments here called change for flight, and these are things that we need to change when we get to the launch site, such as wind speed and things like that. So this here is your seawall pressure, and this will change based on your location on the globe. So this isn't going to be a big thing that changes, but a change of 0.5 will add or subtract like 50 meters, which is quite substantial, so we definitely need to make sure that this number is correct when we arrive at the launch site. So this one is a big one we have to change. Otherwise, we're just defining our inputs, our buzzer, our button, some LEDs. These are our color schemes, I guess, for the LEDs. So when it's waiting, it's going to be green, success green. This should actually be white, but we've been messing around with it as the LED gave us some issues. We have a delay here. We'll go over this delay later. This all has to do with memory here. So we have, again, an Eprom and an SD card. During flight, the computer writes everything to the Eprom. That way it's solid state, and no amount of jiggling or whatever will cause data corruption. However, once we're done with the flight, we need some way to read the code or read the flight data. And so that's what our SD card allows us to do. And once our flight is finished, it'll write all that data to the SD card. So this just helps because we have a 256K sized Eprom on here, and so resetting that each time and writing to it each time is very inefficient. So we have to make saving to it as efficient as possible. Again, I'll talk about this later. This is for the servo. These variables allow us to change where the hatch is because servos are not perfect, and 0 to 90 degrees is more like 0 to 80, 0 to 75. So we added these in, so that way if we change out servos, we're saying we can easily calibrate the 0 and the 1 of 5, which is closed. So if servo max is closed, servo min is opened. Otherwise, again, more variables. These are all go over later. We're setting up our sensors here. These are offsets, so when we turn on the rocket, it takes into account all these. It takes actually the average of all of them, and then sets them, so that way if the rocket has, let's say, a slight tilt, even when it's straight up, that will compensate for that, and it won't think that the rocket's always tilting. It'll just be like, yes, that's normal. Here we're setting up our Eprom, and we're into our setup. So this only runs once. This was all set up here. This runs on. So we're beginning serial, so that way we can read things, and we're beginning our Eprom here. Hatch that attach. Hatch is our servo object, so we're attaching it at pin 23. These are all our inputs and outputs here. This here was, so these 2 bytes, again, I'll explain how this works later. Actually, I'll explain it now. These 2 bytes act as a place, or to know where we stopped the recording, so it only resets up to that point and doesn't reset the whole 256K. So the way we do numbers on here, because Eprom works off of bytes, 8 bits, it saves a number from 0 to 255, or 0 to negative 127, I believe it is. And so it doesn't give us a wide variety, because if we want to store, let's say, more accurate number, let's say 0.25, which is our gyroscope, let's say, or our gyroscope on the x-axis, we can't put a period in there. The period is one character. That's going to take up one storage space. So we need a more efficient way. And let's say we're doing altitude, right? Altitude's going to go above 255, obviously. So this is the way we're doing it. It's not the most efficient way, but it does work, and it allows us to store up to 65,536 numbers. So we have a base and a multiplier, as I like to say. So the way you can think about this is the multiplier multiplies in times of 256. So you can see here. So the multiplier is a number between 1 and 255, or 0 and 255, excuse me. And our base is a number between 1 and 255 also. And the way it works, as you can see here, is the multiplier is multiplied by 256, and then the base is added. So let me just briefly explain how this works. So for the number 1, our multiplier would be 0. 0 times 256 is 0. And then our base would be 1 plus 1. So 0 plus 1 is 1, and that would be 1. Alright, now let's say we have the number 255. Well, we would still use it here in base. So 255, so we'd have a multiplier of 0 again. 0 times 256 is 0, plus 255 would go to 255. And I'll show how we save it, because right now we're just reading, and reading is a lot easier than writing. I'll explain how we write and how we determine what the multiplier is and what the base is later on. So here, with our, let's see where we were. Right, so I'll say we have a number of 512. Now that obviously is greater than 255. So this is where we'd use this multiplier. Actually, let's use 513, so it's not even. So 513 is 256 times 256 plus 1. So our multiplier would be 2, and our base would be 1. So see, we're able to store a number that's bigger than 255 using 2 bytes, right? So we have, again, 512, so it'd be multiplier of 2, 2 times 256 is 512, and then we'd have our base of 1 plus 1, which is 513. And again, this allows us to store up to 65,536 numbers, because if the multiplier is 255, 255 times 256 is some big number, I can't remember, and you add 255, that gets us to 65,536, I believe. That is a quick, brief outline on how that works. Again, when we get to writing, I'll explain that more in detail, but there's that. On here, if we want to reset the EPROM, we do, and this will reset it up to a certain point. This here is just blinking the LED so we know what's going on. The LED is onboard LED, so that way we can see if for some reason the external LED isn't working, we can still see it on the TNC itself. And then we just say starting, set the LED, close the servo hatch, that way the parachute doesn't just fall out. And then here we're storing things. So we're storing the barometer, and if it fails, it blinks an error. We set up the SD card, and again if it fails, and then setting up the gyroscope and accelerometer here. We set these to as maximum as possible, because when we're working with high G forces, I think it exceeds this, but we just need this to be as great as possible. And then here we are saying if there's still data on the chip. So pref max write is looking at those 2 bytes we talked about earlier. Where is it? These 2 here. If these are greater than 0, then there's still data on the flash chip, because it hasn't been reset, and so it tries to upload that to the SD card. So that way, if in case of a flight failure or something, we're able to still retrieve the flight data. Here's what I was talking about with the calibration. Calibrates it here, gets the average, and sets it. Prints it out just for debugging purposes, because sometimes things don't work perfectly. And then we are ready to go. So now we go into the loop. Now this is where it gets a bit complicated, and this is where you need a slight understanding on how C++ works. So instead of staying in a while loop every time we press a button, we're just checking. We have this variable here called flight mode. So flight mode is 0, it's idle, right? And A state is the state of the button. So if it's high, it means it's been pressed. If it's low, it hasn't been pressed. So if A state is high, so we press the button and we're idle, the flight's going to begin initiating. And you see here, we say pre-flight completed is false, and we beep. And that would take us into pre-flight, sort of. We'll, again, explain this later. And you also notice we set flight mode to 1. Now, if we press the button when it's flight initiating, it aborts the flight, stops the flight. Now, once flight has initiated for 5 seconds, it goes to flight mode 2. And again, we'll talk about this later on. Things, you have to jump around a bit, but it just makes sense if we go in order. So just know that after 5 seconds, flight mode gets set to 2. Now, if we press it while it's in flight mode 2, which means the flight has flown and we press it, then it saves the data. And while it's in 3, it's saving data. And finally, once it's done saving data, it sets back to 0. Now this here is similar, except this happens all the time. This happens regardless of whether or not the button's pressed. So when flight mode's 0, right, when it's idle, it does nothing. It's just sitting here. Now, after the button's been pressed, remember, we've pressed the button here. Flight mode is 1. It beeps at us, And now we're stuck in this loop here, right? Flight mode's 1. If pre-flight has not been completed, which it's been, so we set default, so it's going to start this. It's going to go into pre-flight. And pre-flight will set variables and stuff like that. We'll show it later. This code here just blinks the LED. And after, if pre-flight is completed, we set that to true, then it says flight initiated, and you can see here is where we set flight mode to 2. Now, if flight mode is 2, we go into the flight function. We could have done it here, but flight function just makes everything a little more organized and easier to work with. And again, if we press the button, you saw we go into flight mode 3, which is saving data. It's also called post-flight. If post-flight hasn't been completed, it does this. If it has, it goes back to 0 and waiting. It's not too complicated. There's only 4 different modes, because 0, 1, 2, 3, that's 4, if that makes sense. Here we're just getting altitude because it's easier to type get altitude than type this out. So there's that. Average altitude gives a more accurate reading, I guess, because that way, if for some reason wind blows on it or anything, it tends to fix that. However, it's slow. It's about 1 every half a second for some reason. I can't figure out why, because it should be reading hundreds of times a second, but either way, it's not that fast. So we only use this when we really need it. Basically, if got altitude notices the value that we want, then we get the average just to double check, and because that doesn't add that much time on, even though precision is important, and then just to make sure that we're not getting an extraneous number, and then we'll do whatever we need. Acceleration, there's all that. Print data just prints the data. Plot data allows you to plot it on the serial monitor, basically the same thing. And save data. Save data here, if I remember right, yeah, save data saves this to, so we have 2 functions for saving things. We have save data, which saves it to the EPROM, then we have write data, and write data writes it to the SD card. So here is where now this here we can ignore. This is just about the LED blinking. We're going to move down to here. This is where we write data. Now this part here only writes the other flight data. This happens when it's full. You can see here it says completely full. So if the memory is full, we've noticed we're at full memory, it just writes it regardless of anything else. So let's just talk real quickly about writing. So you'll see here, our base is our launch time. So we set base, let's say launch time is 513. We set base to 513. Now you might say, yeah, that's over 255, we can't do that. And that's true. You can see here our multiplier is 0. So now, while the base is greater than 255, so it's going to take the base, subtract 256, and add 1 to the multiplier. What does that mean? Well, let me walk you through it. So let's say we have, again, the number 513. Is 513 greater than 255? Yes, it is. So base is now 513 minus 256. Okay? So now base is 257, and multiplier is 1. Now is 257 greater than 257, 256? That'd be 257. Yeah, it'd be 257. Is 257 greater than 255? Yes, it is. It is. So we're going to take 257, subtract 256, and now base is 1, multiplier, again, we add. This means add, so multiplier is now 2. And our base is 1, and 1 is less than 255, so we exit this. So now we have a multiplier of 2 and a base of 1, and if you remember earlier, that's exactly what we want, because 2 times 256 is 512, plus 1, which is the base, gives us 513. Perfect. And then you can see here we write that. So we're writing all these. These are just other things, flight data, when we reached apogee, when we released our parachute, and everything like that. And then this here, went down a little too far. This here is where we're actually writing our data. So this here is flight time, get altitude, and everything like that. And then, so each write cycle is a block, we'll call it, I'm going to call it a block, of 16 bytes. So every 16 bytes is a new period of recording. And in that 16 bytes, you have altitude, you have acceleration, things like that. Alright? So, each block is what we're calling again a cycle. And each cycle, again, like I said, 16. So we have these offsets, right? We start at 1 and 2 is here, 3, 4, 5, 6. So for the first block, we're writing this at 1. Right? The second block, we're writing it at 17. Third block, we're writing it at 33, and so on, so on. And the point is that we know where this is always at. So if we need an exact value, we know it's going to be at write cycles times 16 plus 1. Same thing down here. And so these all go up to, again, should you go to 16? Yeah, it does. 1 to 16. Because 0 is used for some other thing, I think. I can't remember. Anyway, that's how that works. Hopefully that made sense. I'm sorry if it didn't make total sense. But just know that each time the computer writes data to the EPROM, it writes all of the sensor data at the same time, which is 16 bytes worth of data, and then it creates a new cycle, so we move on to this next chunk. Writing data is way simpler. This is for the SD card, so we write it from the EPROM to the SD card. So all we do, like we did earlier, we take the data. For time is written, again, everything here is written as whole numbers, as integers. Time, we need a decimal because we want seconds. So we take this, we divide it by 1,000 because it's done in milliseconds, and we are given the seconds. Same thing here with acceleration. Acceleration, we're writing, let's say, 2429, right? That's 24.29, but we can only save it to the thing as 2429. So on here, we have to divide by 100, so that we get 24.29. And it saves this all. And once it's done writing, it closes the file, saves it as a CSV. Then it opens a text file, and this, like I mentioned earlier, gives us launch, apogee, parachute deployment. And this just makes it easier so we don't have to scout through tons of stuff to see where these important flight events happen. And if it fails and yells at you. Same here. These final things are pretty quick. This is just LED. We have two sets for digital pins, for analog pins. Originally, I had a really nice LED that was RGB LED that was working great, and I had it in analog pins. Then while soldering the second version of the Shoot flight computer, I couldn't reach the analog pins because of the way I designed it, which wasn't great, but it's fine, and so I used digital pins. And then the third version, I was able to use analog pins, but for some reason I was trying to use a different LED because it fit better, and it would not work with analog. I do not know why. It makes no sense to me still, but who knows. So we had to end up using digital on that, which is fine. It's not a big deal. But analog is nice because you have a whole color spectrum instead of just red, green, or blue. And I mean, you can combine them, but it doesn't look great. Here's pre-flight, like we talked about earlier. Pre-flight will last for 5 seconds regardless because I want 5 seconds to be able to work with things. Here, it again makes sure the hatch is closed. So if it's been 5 seconds, it does this. Otherwise, it just does this because pre-flight doesn't take long. And again, pre-flight is mainly just hold it for 5 seconds, make sure that I don't want to abort it, and then start the flight. And as you can see here, once it's done, it's been 5 seconds, make sure the server is closed, and starts all this stuff. Yeah. Flight here, this runs repeatedly while the flight's going on, and this again gets a little more complicated, but it's not too bad. So this we have flight stage. This is not flight mode, this is flight stage. So this happens when flight mode is 2. Flight stage is 0. So flight stage 0 is very strict, hasn't launched yet. Now we used to do launch detection by acceleration, however, just to make sure that wouldn't fail on the first flight, we decided to do a timer. So that code's actually gone. I'm surprised I deleted it and didn't just comment it on, but it's gone. So you just say if acceleration y, or whatever axis it's on, is greater than a few g's, then start the flight. But for now, we just have a timer. And it beeps at you a ton, as you can see here, for 10 seconds. And then it goes to flight stage 1. So this is after it is detected launch, quote-unquote detected. In this case, it's just after a launch has started. Now it starts looking for one or two things. Whether we're at the right altitude and we really need to recover the parachute, or whether we can make sure the parachute opens at the right time. So for the first flight, we added this code here, which would basically just recover the parachute the minute it noticed descent. And that way, if for some reason our code for finding the best position to open the parachute at didn't work, it wouldn't be a big deal. So, and then after the first flight, if it worked, because we can again look at the flight data, which is very nice. So if it worked, then we'd be like, okay, it worked, and we would just get rid of this line. But anyway, we'll talk about this because why not? It just checks to see if should recover. If so, it says absolute reach because it notices that the altitude starts going down, and it has to be within this because again, if for some reason there's a false positive low on the ground, we don't want that to affect anything. So we have to be within this, which does bring up the fact that if for some reason the rocket flies horizontally, the parachute won't open. But that hopefully won't happen. Famous last words. Anyway, we also have another emergency thing here. If it's been 15 seconds since launch has been detected, and it still doesn't think it's a good time to open the parachute, open it anyway. And this is because if for some reason the code doesn't work, the altimeter breaks, something breaks, the parachute needs to open. I really do not want to lose, $50, $100 worth of electronics. That would not be fun. And the whole rocket, too, that took hours to build. So that failsafe is just in there. So if it's been 15 seconds, right, and our apogee is expected to be reached around 7 to 8 seconds. So that gives it double the time. And if it were to not open the parachute, it lands around, I want to say 25 seconds, 30 seconds. No, definitely 25, 20 to 25. So it's cutting it close, but just make sure that we get that parachute open. And then finally, here's check course. We'll go over this at the very end. I don't know too much about this because I am not in physics. Rylan is taking physics outside of school, so he made a video on this, I believe, talking about how this works. But I'll show you the code at the bottom. Anyway, once we decided that yes, this is what we want to do, we open the parachute. Hatch that right, server min. And just in case for some reason it got jammed, we try a second time. Even if it worked the first time, it doesn't hurt. Flight stage 2 here just says parachute deploying. This was used earlier. Yeah, you can see here flight stages 2, and that way, emergency recovery, it goes out of this loop, comes into this one, and it deploys the parachute. And finally, flight stage 3, it says to 200 delay MS. So delay MS, I forgot to mention this, is how fast it's reading or writing data. Reading from the sensors, writing the data. Because if we are sitting on the launch pad, we do not need to be reading and writing as fast as we can. Right? We're sitting there. We just need to be writing fast enough so that the minute launch is detected, we can start really making sure that we are putting in the data. And again, this was designed earlier when we didn't have much EPROM space and we really needed to save it. Same thing, when coming down on our descent, we're not doing anything. We're just coming down. So we only need to write maybe once or 5 times per second. We don't need to be writing 20 times per second, which should be what it's writing normally. And then once it's done, or not when it's done, when it's running this in flight, because this is still in flight, save data, which is saving it to the EPROM. Post-flight, here's post-flight. You'll notice there's actually no delay and no timer on here. This just waits until it's been able to write all the data to the SD card, which can take some time before saying it's done, beeps at you, and is post-flight complete as true. EPROM, reset EPROM, again, it only resets it, and resetting by setting it to 0, up to prefmax write. So again, here's the write cycles, and it writes it up to that. And then it resets also all the other data, such as apogee reached and everything like that. Finally, we are at the end, 20 minutes later. And this is Rylan's code. So this checks the course, and if we want to open it, returns true. That's about it for the code. Sorry for the lengthy explanation, but there's just a lot in here to cover in terms of making sense of all of it. It does seem very complicated, but there's a lot in here that doesn't really need to be said. That was still said anyways. But yeah, with that, that's all. Thanks for watching. See you next time.